You ever stop to think about how one tiny single atom, just by being in a slightly different spot, can completely change everything? How it can be the difference between the fuel that runs your car and the sugar in your morning coffee? Well, let's dive in and see how a single oxygen atom creates two totally different but totally essential families of molecules.
So, to kick things off, let's chew on this question. At first glance, beer, gasoline, and sugar, they couldn't seem more different, right? One's for a night out, one gets you to work, and one makes your food sweet. But believe it or not, chemically, they're all surprisingly related.
And there's your answer. The secret sauce that connects them all is just one single oxygen atom tucked into a simple molecule. But where it's tucked in, well, that makes all the difference, creating things with wildly different properties. So here's our game plan. First, we're going to see how that one atom creates two distinct molecular families. Then, we'll meet the alcohols and learn the simple code for naming them. After that, we'll get introduced to the ethers. And we'll wrap it all up by seeing how this chemistry is playing a massive role inside your own body. All right, let's get into it. When we take a basic hydrocarbon, that's just a molecule made of carbon and hydrogen, and we add an oxygen atom, we get what's called a hydrocarbon derivative. Think of it like taking a basic cake recipe and adding either cinnamon or a lemon zest. Same base, but a totally different outcome. Now, the key to understanding all this is a concept called a functional group. The best way to think about it is that it's the molecule's personality. It's the active part that does all the cool chemical reactions and pretty much defines what that molecule is all about. And in our story, oxygen is the star of the show.
And this slide just lays it all out perfectly. It's so simple, but so powerful. If that oxygen atom is hanging off the end, attached to one carbon and one hydrogen, you get an alcohol. But if that same oxygen atom gets sandwiched right in the middle of two carbons, acting like a bridge, you get a completely different beast, an ether. Same parts, different setup, totally different world. So let's zoom in on that first family, the alcohols. What are they, really, and where do we bump into them every day? The official definition is pretty straightforward. An alcohol is what you get when a hydroxyl group, that's just one oxygen and one hydrogen, the famous OH, kicks out a hydrogen atom on a hydrocarbon and takes its place. That little OH group is the functional group for every single alcohol. It's their calling card.
Now here's a really important point. You see that OH, and you might think of bases, like sodium hydroxide, but they're not the same at all. In an alcohol, that OH is locked onto a carbon atom with a strong covalent bond. It doesn't just pop off in water, and that's exactly why alcohols are not bases. And this family is incredibly diverse. You've got ethanol, right? That's the one in beer and wine. But then you have ethylene glycol, which you definitely don't want to drink. It's the main ingredient in antifreeze. And then there's glycerin, a thick, syrupy alcohol that's used in stuff like cosmetics to keep them from drying out.
Okay, those names might look a little intimidating, but I promise there's a really simple logic to them. Let's quickly break down the naming system so you can basically decode them yourself.
It's really just a three-step recipe. First, you find the longest chain of carbons. 5 carbons is pentane. Easy. Step 2, because it's an alcohol, you just drop the E from the end and add ol. So pentane becomes pentanol. And finally, you just add a number to say where that OH group is. In this case, it's on the second carbon, so 2-pentanol. See? Simple.
All right, time to meet our second family. We've seen what happens when oxygen hangs off the end, but what happens when it's right in the middle, connecting two carbons? Well, that's when we get the ethers.
So an ether is all about its functional group, that oxygen atom acting like a link in the chain between two carbon groups. Remember that bridge analogy? That's an ether. Instead of the OH group on the side, like an alcohol, the oxygen is smack in the middle. That structure is everything. And ethers are super useful. They're fantastic solvents for sticky things like waxes and fats. And one of the most famous ethers in history, diethyl ether, was actually a revolutionary anesthetic, first used way back in the 1840s. These days, you'll find an ether called MTBE added to gasoline to help it burn cleaner. Okay, so we found alcohols and ethers in our cars, our drinks, our history books, but it turns out their most important job is way, way closer to home. That's right. This isn't just some abstract chemistry lesson. This stuff is fundamental to how your body is working this very second, at the deepest molecular level. And here it is, the big reveal. Carbohydrates, sugars, they are built using these exact two functional groups. If you look at a sugar molecule, it's just covered in alcohol. or negative OH groups. And when your body links sugars together to store energy, it connects them by forming an ether bond. It's amazing. The very architecture of our food energy is just alcohols and ethers.
So this simple chemistry is the very basis of metabolism. It's how your body gets energy out of every piece of bread or fruit you eat. But it's a very delicate system. And when the body's ability to manage these sugar molecules gets out of whack, the results can be really serious.
I just want you to take a second and look at this number. 380 million. It's a huge number, and it represents a global health crisis that is directly tied to the simple chemistry we've been talking about.
That was the number of people estimated to have diabetes worldwide way back in 2013. And diabetes is, at its core, a disease about the body's struggle to process sugars, those molecules built from alcohol groups in ether linkages. It's just a powerful, real-world reminder of how much this tiny molecular stuff really matters.
Which, brings us right back to where we started. One simple oxygen atom, placed in one of two spots, gives us everything from antifreeze to anesthetics to the very fuel that runs our bodies. It really makes you wonder, doesn't it? What other incredible secrets are just hiding in plain sight, in the simple ways that atoms are arranged all around us?